Hi guys. Okay, today we're going to look at writing the equation of a tangent line and a normal line. Now they're both equations of lines, so we use our favorite form of the equation of a line, the point slope form, y minus y1 equals m times the quantity x minus x1. Now almost always when we're doing these problems, the x value has been given to us. Once we know the x value of the point, in order to find the matching y value, we plug the x into the original function. That will find us the matching y value. Then, to find the slope of a tangent line, we substitute the x into the derivative because the derivative is the slope of the tangent line. So let's try this example. We did on a previous day, we used the definition of derivative to find that f of x equaling x squared plus 3x, that its derivative would be f prime of x is 2x plus 3. So now we want to find the equation of the tangent line to f of x at x equals negative 1. So notice there's our x value, negative 1. So whenever we want to do a tangent line, it's y minus y1 equals m times x minus x1, and we need three pieces of information. We have the x value. We need to find the y value. We find the y value by plugging the x value into the original function. So we would have negative 1 squared plus 3 times negative 1. So that's 1 minus 3. Or negative 2. Now we know our y value. Then the third piece of information is the slope of the tangent line. Now the slope of the tangent line, we take the x value and we plug it into the derivative. So this time it's 2 times negative 1 plus 3. So negative 2 plus 3, or just 1. So now we have y minus our y value is a negative 2, so that becomes plus 2, equals our slope is 1 times x minus the x value, which is negative 1, so that becomes plus 1. Now we don't usually write a slope of 1, so if you leave it like this, that's perfect. If you want, you can subtract the 2 from both sides and tell me y equals x minus 1. But remember, the more algebra you do, the more room you have for careless mistakes. Now, in part B, we want to find the equation of the normal line. Now, before we can do that, we have to make sure you know what a normal line is. A normal line to a curve is the line perpendicular to the tangent. Okay, so a normal is perpendicular to the tangent, but what do you know about perpendicular lines? They have negative reciprocal slopes. So the slope of a normal line is a negative reciprocal slope of a tangent line. So we already know if we're doing this at the same x value at negative 1, the y value doesn't change. It's still f of negative 1, which we already found is negative 2. But now the slope of the normal is the negative reciprocal of the slope of the tangent that we found up here. So the negative reciprocal of 1 is negative 1 over 1, or just negative 1. So now the equation of our line is y minus our y value is negative 2, so plus 2, equals our slope is a negative 1 times the quantity x minus our x value is a negative 1, so it becomes plus 1. And here's the equation of your normal line. Perfect. Now the next part is asking us to put this in the calculator and to graph it. So just a little note here, when you go to put this in, let's say f1 would be the function, f2 would be the tangent, so probably f3 of x. We would have the negation of the x plus 1, and then you just have to remember to subtract the 2 over to the other side. You do not need to distribute the negative and combine like terms. Again, that's more places to make those careless, silly mistakes. So now we're going to go to our calculator and we're going to take a look at this. Okay, so here we are at a calculator. The first thing we're going to do is we're going to graph our function, which was x squared plus 3x Then I'm going to go down to F2 and we're going to graph our tangent line, which was y equals, or f of x equals x minus 1. And then in F3, we're going to graph our normal line, which is f of x equals the negation of x plus 1. Don't forget to close the parentheses, and then minus 2. Enter. And then we were told to zoom, so we're going to go to Menu, Window, Zoom, and we're going to zoom square. And the reason we zoom square is so that you can actually get a better view at how these two lines, your red tangent line and your black normal line, are perpendicular. If you're not in a square window, you won't actually see that. Okay, but now you can see they have that point of tangency. All three graphs are meeting at that same point where x is -1. And you can see that the tangent and the normal are perpendicular. Okay, we're going to go back to our other document. Okay, back from the calculator, and here we go. So let's look at this next question here. An equation for the line tangent to the graph of the differentiable function f at x equals 3 is y equals 4x plus 6. So this is the equation of the tangent line. Which of the following statements must be true? Do we know that f of 0 equals 6? Do I know anything? I know that this point 0, 6 is on the tangent line, but it doesn't have to be on my function because my function only has to touch the tangent line at this point. So I don't know that this one has to be true. Does f of 3 have to be 18? Now, if we think about this for a minute, if the tangent line and the function meet at the same point where x is 3, if I plug 3 into the tangent line to find the y value of the tangent line, it's also going to be the y value of the function because they're at that same point. So if I do 12 plus 6, I do get 18. This one is true. Now, does the derivative of at 3 have to be 4? Well, here's the thing. The derivative is the slope of the tangent line. Is 4 the slope of the tangent line at x equals 3? Well, if you look at the tangent line, that slope is 4. So yes, this one is true. So 2 and 3 have to be true statements, but I know nothing about f of 0. Okay, let's look at the next one. Let f be a differentiable function with f of 1 equal to 3. The graph of f prime of x is given here. Which of the following statements is true about the line tangent? So we're looking at the tangent at x equals 1. Now, as soon as I hear tangent lines, I go x1 equals, y1 equals, and slope equals. Well, we're looking at the tangent line at x equals 1, so that's my x value. I find the y value by finding the function at 1. Well, they told me that. That's 3. I find the slope of the tangent line by plugging the x value into the derivative. Well, they gave me the graph of the derivative. And when x is 1, what's the height of that derivative? It's 2. So I got all this information without even looking at my choices. I know that my slope is 2, and I know that I'm passing through this point 1, 3. Well, does that match anything we have here? It's not a slope of 0, not a slope of 0. Here we have slopes of 2. And which was the point? 1, 3. This is the one we want. Okay, good. Now I'm going to go over to the calculator and I want to show you a document that I have there called Derivative Trace. And we're going to talk a little bit about some things and then we're going to come back and write down some conclusions that we find. Okay, here we go. Okay, guys, so here I have a document called Derivative Trace. And what we have is you can see we have a nice little graph here. It's a cubic, and you can see that there is a tangent line, and the point of tangency is when x equals a. Now, I'm going to have the same graph on this window. Only now, not only do I have a here, but at this point A, P represents the slope of this tangent line. And you can see as I drag this point, P is moving. Now notice over here, the function is increasing and P, notice there it is, but it's positive this whole way. And when we get to the top here at the maximum, we have a horizontal tangent line and P is at 0. Now we come down here, our slopes are getting steeper, but they're negative, so P is going down. But now they're getting less steep and P is coming up until all of a sudden we're at the minimum and P is 0. And now as our graph is increasing, we have a positive slope again. P is positive. Now, when I change the page, it's going to look very familiar again. It's the same picture. Only now I have it set up that when I drag this point A, P is going to move, but it's going to leave a trail. So this time it's going to plot, it's going to leave a trail of every place it's been, every height that the slope was. So what we're graphing is all the slopes. What is that? What function is that? If we plot at each of these x values the slopes of the tangent line, remember the slopes of the tangent line are the derivative. So this graph is the derivative of the original one. And notice how every place the function was increasing, the derivative is positive. When the function is decreasing, the derivative is negative. When the function is positive again, when the function is increasing again, the derivative is positive. Those are all the points that I dragged it at. Here's another one, okay? So we start off really steep negative slopes. They're coming up. Wait a minute, what happened right there? Notice it jumped, but there was a corner. See that corner, that sharp corner? There was a corner on the graph. And now our derivative's not connected. That's because there's no derivative where there's a sharp corner. And I keep dragging and I keep dragging. There's my derivative. I'm decreasing, so it's negative. I'm still decreasing, so it's still negative. And whoops, I got to a corner and it jumped again. Increasing, decreasing, corner, and it jumps. And then I have, see, look at that. It's not connected. It's in 1, 2, 3, 4 different parts, this derivative. But notice there's 1, 2, 3 different sharp corners, okay? And when there was a max, we were at 0. When there was a max, we were at 0. Here's another one. This time, I'm going to have a problem trying to get my A. My P is right on top of my A. I must have left this kind of weird the last time I used it. I don't know if I can grab A. I can't grab point A. There it is. Okay. Getting steeper and steeper and steeper. It's increasing and getting steeper and steeper till it's off. Now notice I'm at a vertical asymptote where I have a vertical tangent line which has no slope. And then all of a sudden I'm jumping to the other piece. And notice this now. I'm getting, here we go. And now when I'm at 0, and then I'm decreasing, and now we're negative, and I'm coming up to another vertical asymptote. So my derivative jumps, and there it is. That's a very cool derivative. Look at that. Funky. This one, notice this is a sine graph, right? And if I drag this, notice what we get. The derivative of sine is, do you recognize it? Cosine. Woohoo! So we'll stop right here. Let's go back and write down some things that we observed while looking at these graphs and their derivatives, okay? Okay, so what did we learn? We learned that when the derivative of f of x is greater than or equal to 0, that means that our function f of x is increasing. When our derivative f prime of x is less than or equal to 0, and notice, yes, they both have an or equal to on them, f of x is decreasing. We also noticed that when the derivative is 0, f is horizontal, and you have a possible location for a max or a min. You are not guaranteed a max or a min just because the derivative is 0. The function has to change from increasing to decreasing or decreasing to increasing, which means your derivative has to change sign. If the derivative does not change sign, you will not have a max or a min. Now, there is another two things that we want to keep in mind here. When f of x has a corner, so a sharp corner, the derivative does not exist. When f of x is vertical, so it has a vertical tangent line, the derivative does not exist again. Okay, so those are the important things to take notice of. Now, some relationships between the graphs of f and f prime, some things to take note of.